Voltage drop is a fundamental concept in electrical circuits, representing the decrease in electrical potential along the path of a current flowing in a circuit. Understanding voltage drop is crucial for ensuring the proper operation of electrical devices and systems. The basic formula for calculating voltage drop is volts equals current times resistance, or volts equals I times R, where volts represents the voltage drop, I represents the current in amps flowing through the circuit, and R represents the resistance in ohms of the conductor or component causing the voltage drop. This formula is derived directly from Ohm's law, which describes the relationship between voltage, current, and resistance in an electrical circuit. To effectively utilize the voltage drop formula, it is important to correctly identify and quantify the current and resistance values relevant to the specific circuit segment under analysis. The current value represents the amount of electrical charge flowing through the conductor, typically measured in amps. The resistance value represents the opposition to the flow of current, typically measured in ohms. The resistance of a conductor is influenced by several factors, including the material of the conductor, its length, and its cross-sectional area. Longer conductors and conductors with smaller cross-sectional areas will exhibit higher resistance. When applying the volts equals I times R formula, it is essential to ensure that the units of measurement are consistent. Voltage should be expressed in volts, current in amps, and resistance in ohms. If the units are not consistent, appropriate conversions must be performed before applying the formula. For example, if the current is given in milliamps, it should be converted to amps by dividing by 1000 before using it in the formula. It is also important to consider the total resistance of the circuit segment when calculating voltage drop. This may involve summing the resistances of multiple components connected in series within the segment. In more complex circuits where components are connected in parallel or in a combination of series and parallel configurations, the equivalent resistance of the circuit segment must be determined before applying the volts equals I times R formula. The voltage drop formula is a powerful tool for analyzing and designing electrical circuits. It allows engineers and technicians to predict the voltage drop that will occur in a circuit under various operating conditions. This information is essential for ensuring that electrical devices receive the appropriate voltage to operate correctly. Excessive voltage drop can lead to a variety of problems, including reduced performance of electrical equipment, overheating of conductors, and even complete failure of the circuit. By carefully calculating voltage drop, it is possible to select conductors and components that are adequately sized to minimize voltage drop and ensure reliable operation. In practical applications, several factors should be taken into account when calculating voltage drop. Firstly, the temperature of the conductor can affect its resistance. As the temperature of a conductor increases, its resistance also increases. This effect is more pronounced in some materials than in others. Therefore, it is important to consider the operating temperature of the conductor when calculating voltage drop, especially in high current applications. Secondly, the type of conductor used in the circuit can significantly affect voltage drop. Different materials have different resistivities, which is a measure of their resistance to the flow of current. Copper and aluminum are commonly used as conductors in electrical circuits due to their relatively low resistivities. However, even within these materials, there can be variations in resistivity depending on the purity and processing of the material. Thirdly, the length of the conductor is a critical factor in determining voltage drop. As the length of the conductor increases, the resistance also increases proportionally. This means that longer conductors will experience a greater voltage drop than shorter conductors carrying the same current. Fourthly, the cross-sectional area of the conductor affects its resistance. As the cross-sectional area of the conductor increases, the resistance decreases. This is because a larger cross-sectional area provides more pathways for the current to flow, reducing the opposition to the flow of current. Therefore, conductors with larger cross-sectional areas will experience a smaller voltage drop than conductors with smaller cross-sectional areas carrying the same current. To minimize voltage drop, it is generally desirable to use conductors with low resistivity, short lengths, and large cross-sectional areas. However, These factors must be balanced against other considerations such as cost, weight, and space constraints. In many electrical installations, voltage drop is limited by codes and standards to ensure safe and reliable operation. These codes and standards typically specify the maximum allowable voltage drop for different types of circuits and applications. For example, the National Electrical Code, or NEC, in the United States provides guidelines for voltage drop in branch circuits and feeders. The NEC recommends that the voltage drop in branch circuits should not exceed 3%, and the voltage drop in feeders should not exceed 5%. These limits are intended to prevent problems such as reduced lighting intensity, decreased motor performance, and overheating of electrical equipment. To comply with these voltage drop limits, it is often necessary to use larger conductors than would otherwise be required based on the current carrying capacity alone. The voltage drop formula can be used to calculate the required conductor size to meet the code requirements. In addition to the basic volts equals I times R formula, there are other more complex formulas that can be used to calculate voltage drop in alternating current, or AC, circuits. These formulas take into account the effects of inductance and capacitance which can affect the voltage drop in AC circuits. Inductance is the property of a circuit that opposes changes in current, while capacitance is the property of a circuit that opposes changes in voltage. In AC circuits, inductance and capacitance can cause the voltage and current to be out of phase, which can affect the voltage drop. The voltage drop in AC circuits can be calculated using the following formula: volts equals I times Z, where Z is the impedance of the circuit. Impedance is a measure of the total opposition to the flow of current in an AC circuit, and it includes both resistance and reactance. Reactance is the opposition to the flow of current due to inductance and capacitance. The impedance of a circuit can be calculated using the following formula: Z equals the square root of R squared plus X squared, where R is the resistance of the circuit and X is the reactance of the circuit. The reactance of a circuit depends on the frequency of the AC voltage and the values of inductance and capacitance in the circuit. In many practical applications, the reactance of a circuit is small compared to the resistance, so the voltage drop can be approximated using the volts equals I times R formula. However, in circuits with significant inductance or capacitance, it is important to use the volts equals I times Z formula to accurately calculate the voltage drop. The voltage drop formula is an essential tool for electrical engineers and technicians. It allows them to design and analyze electrical circuits to ensure that they operate safely and reliably. By carefully calculating voltage drop, it is possible to select conductors and components that are adequately sized to minimize voltage drop and prevent problems such as reduced performance of electrical equipment, overheating of conductors, and complete failure of the circuit. Remember that factors like conductor temperature, material, length, and cross-sectional area all play a role in determining the overall voltage drop within a circuit.